Okay, so what are the contents we'll cover in this course? The contents are, first we'll talk about introduction, then analysis of power system stability by classical methods, then modeling of synchronous motion, modeling of exciter, turbine, and load, then representation of synchronous motion for stability studies, then small signal stability analysis, and transient stability analysis, and voltage stability analysis. So these are the contents we'll cover in your course, and the first 4 modules I will take, like introduction, analysis of power system stability, the classical methods, then modeling of synchronous motion, modeling of exciter, turbine, and load. Then rest 4 modules will be taken care of by Dr. Siva Subramanian. Representation of synchronous motion for stability studies, small signal stability analysis, transient stability analysis, and voltage stability. So up to mid-sim I will take these 4 models, then rest whatever possible amount will finish. Then after that Professor Siva will take and he will finish the course. So so as we are planning within after this 4 module is over, we'll have one presentation of a term paper, and then your mid-sem exam. Okay. Okay. A little bit we can discuss about the introduction. We know about the power system and the historical background. What this power system actually, we know very well that that power system is a very huge system, right? And generally it is a gradual evolution of from a small system, as you can see here. We'll see just little historical background. In 1882, the first complete electric power system was developed by Thomas Edison, and that was known as Pearl Street Station. This generating station, named as Pearl Street Station in New York, and Thomas Edison was actually the first innovator of this system, and it was in fact a DC system, right? In 1884, development of DC motors by Frank Sprague came into picture. Because as the DC power system came into picture, so during that industrial revolution, in fact we can say it is the second industrial revolution. And in that industrial revolution, electricity is being used, because in first industrial revolution only steam engines were being used, and this is the second industrial revolution where electricity came into picture and it is being used in the industry. So in industrial application mostly we use the motor, so therefore this DC motor was developed in 1884 by Frank Sprague. So then certainly there are certain disadvantages was found in the low voltage DC system. And of course we know when the transmission line is long, there are transmission losses and voltage drop in the system. In 1886, development of transformer and AC transmission system came into picture. So this actually created a revolution after this AC system came into picture. In 1888, development of AC polyphase system and transformers by Nikola Tesla and all the patents were brought by the Westinghouse company. The Westinghouse is a big company which actually purchased all the patents by Nikola Tesla, which is based on the AC polyphase system and the transformers. So this actually helped to step up the voltage to a very high value, and it is being transmitted over the transmission line. So the first AC transmission line in USA, it is from Oregon to Portland. There was 21 kilometer and rated at 4 kV was installed. And it was tested and installed. Then in 1890, there was a debate over the standardization of electric supply system, because in many places they started using DC, and in many places they started exploring the AC system. So therefore a standardization is required, because without the standardization the interconnection is very difficult. Okay. So therefore the standardization of using the electricity supply system became very important. So therefore many debates took place. So finally AC system won over the DC system, of course, because of the many advantages, and the important two advantages were that voltage levels can be easily transformed using the transformers, and AC generators and motors are much simpler and cheaper. If you'll see the constructional aspects or the design aspect of the AC generators and motors, they are much more simpler and cheaper than the DC generators and motors. It also requires less volume as compared to the DC machines. So therefore, AC system won over the DC system because of these advantages. And as the voltage level is increased or transformed to a high value, so when it is transmitted over long transmission line, the losses were very less, losses were decreased, and also the voltage regulation was enhanced. Then in 1893, the first three-phase line in USA, it was installed. It was 12 kilometer, 2.3 kV. Then many different frequencies were in use during those days: 25 Hz, 50 Hz, 60 Hz, 125 Hz, 133 Hz. And that in fact posed a problem for interconnection. And finally 60 Hz was adopted in USA, and 50 Hz in many other countries, including India. So, in India we have 50 Hz system. So, then high voltage power transmission system was devised gradually. It was developed because because of the reduction of losses and improving the voltage regulation. So earlier power is transmitted at various voltage levels: 60 kV, 165 kV, 220 kV, 287 kV, etc. And later it was standardized to 115 kV, 138 kV, 161 kV, 230 kV. It is in USA, right? And for long distance bulk power transmission, ESB system was devised. That is 345 kV, 500 kV, and 765 kV. But in India, we adopt the following standards: 132 kV, 220 kV, and 400 kV, then 765 kV. So most of the transmission lines in India, we found it is 400 kV, and few are 765 kV. And others are, of course, 220 kV and 132 kV level. They are of sub-transmission level. Then gradually the time came to develop the HVDC system, high voltage DC system, We know previously the DC system was rejected, but it was found that high voltage DC system has a certain advantage over the high voltage AC system. So when we consider characteristic economic cost versus distance, it was observed that high voltage DC system has certain advantages. We can see here in this figure that of course both sides we are getting AC, and in between we have the high voltage DC line, where high voltage DC line is connected through the converting station. And that converting station in fact converts AC to DC, and at the receiving end it converts DC to AC. This is high voltage DC system. So therefore we require two converting systems at the sending end, one converting station that is, and that converts, in fact in both way, whenever the power flow is in opposite direction it converts DC to AC. In the forward direction it converts AC to DC. So we need a bi-directional converter at both the sides, right? So this is the DC HVDC system. Therefore, the cost is of course increased, but for a long transmission line, it was reduced. Why use HVDC system? The one is your break-even distance. So break-even distance, and other one is your synchronization of the systems having different frequencies. So break-even distance is the distance where actually, if we plot the cost versus distance for both high voltage AC transmission system and high voltage DC transmission system, we'll find both will intersect at a point where actually the cost of HVDC system gradually it will settle down, saturate, where the HVAC system it will increase more and more as we increase the distance. So that is known as break-even distance. And so therefore when the distance of the transmission line actually is beyond the break-even distance, is above the break-even distance, at that point we should choose HVDC system because of the lowering the cost. Then another advantage of the HVDC system is synchronization of the systems having different frequencies. If we have two systems of different frequencies, one is 50 Hz, other one is 60 Hz, it is difficult to synchronize, but through the HVDC system, we can easily synchronize these systems. That is, we have seen the cases in Japan, and there are two islands, they are operating in different frequencies. They are interconnected through this HVDC system. Okay. This is what we can see from the historical background. This is the structure of a typical power system. So we know this very well that these are the major components of the power system: generation, transmission, sub-transmission, and distribution. And the distribution lines are connected to the end users, the industrial loads, commercial loads, domestic loads, and agricultural loads. And sometimes these users, like industrial loads and commercial loads, they're directly connected to the sub-transmission line. That is 132 kV or 220 kV. Like IIT Patna is also connected to a 132 kV system. And we have a substation here which actually converts 132 to 11 kV. And 11 kV is being transmitted throughout in a ring network. It is supplied in our campus. So now ours is 33 kV and 11 kV, sorry, 33 kV and 11 kV. And 11 kV is being supplied in the ring network, and in the secondary substations it is being again stepped down from 11 kV to 440 volt. Okay, so this is we can see the generation. In generation we can have synchronous generators, induction generators, DC generators, and they may be renewable and non-renewable type. Okay, and of course the EHV transmission system is 400 kV and 765 kV, and generally the HVDC system is rated at 500 kV. Okay, and then the sub transmission system as well. So this is your typical structure of a power system, and the power system is very huge network. It is like, if you see, it is like a ocean. So somewhere there is some disturbance, like we see in the ocean. There are certain waves they come, and it comes because of the disturbance created because of the wind, right? So therefore, sometimes whenever there is a disturbance, it is operating with high inertia, and with certain disturbance, sometimes it becomes disturbed, but again it stabilizes. So therefore, we'll read that. We'll gradually study about those things. First, we'll talk about the classical methods, and then we'll gradually move. These are the subsystems of a power system and associated control. We can see here in the transmission controls, the reactive power and voltage control, HVDC transmission associated control. So where the generator power, type, flow, and frequency, they need to be fed back to the generator control, where it is being fed as the feedback signal, and then the generation is being controlled through that. Then the generation is controlled, and similarly, if we have many generators, right, here only one generating unit is shown for the control purpose, and similarly, if we have many generators, simultaneously they take control actions, right? We are discussing power system operating states, right? And we discussed this 5-state model, where in the normal state, this is LO constant. This LO constant actually it is not violated under normal condition, normal operating condition. This L is your line constant, okay, and O is your operating constant. The line constant means your and the operation is happening without violation of the line limits, like your thermal limits, stability limits, right? Loadability limits, right? And your operating constraints, these are based on the, and without any violation of voltage and voltage angle, right? Voltage magnitude, all these things. So these are the operating constraints. So therefore, this L and O, they remains intact in normal operating condition. Like normally when we operate around the load flow for the base case, generally no violation we see, right? The voltage, magnitude, angle, power flow, they all remain within the limit. And as soon as there is a disturbance, of course, the system goes to the alert state. And under alert state, this L and O are not violated, but it is at the verge of the limit. That means what is the limiting value? So it verges, whether the line constant or operating constant. But As soon as again from alert state, if some remedial action is taken, then it can go back to normal state. Or if the remedial action is not taken, then it will go to the emergency state. Okay. So under emergency state, I think somebody. Okay. Under emergency state, your operating constants are violated. Okay, L and O. O is violated, but L is not violated. And again, in the emergency state, if some remedial action is taken, then it can go back to alert state. If not so, then it goes to in extremis state, where both L and O, they are violated. Line constant and operating constants are violated. And from in extremis state, it is not possible to go back to alert state or normal state. So therefore, we need to take the restorative action. This restorative action needs to be taken. So therefore, this state is known as restorative state, where the restorative action is taken in various ways. Because when the power system reaches the in extremis state, we can say that the power system is under blackout. So therefore, this in extremis state can be achieved from alert state, or it can be achieved from emergency state. Okay. And from here, it goes to the restorative state, where the restorative action is taken. And from restorative state, it can achieve the alert state or the normal state directly. This is restorative state. When the blackout occurs, the restoration process, it takes a long time, but it is called, these are called the restorative states. So these are the five-state model of power system. Okay. The power system control hierarchy we already discussed. This is from pool control center. Then it gives the control signal to system control center. Then the transmission plants and power plants, already discussed these things. And the pool control center, basically in India we have many pool control centers. Like we have various power pools. We have different regional power grids. Like in India, we have 5 regional power grids. Okay. And they're based on this principle, they work, they create the pool control center. Okay. 5 regional load dispatch centers. Of course, they're now known as the POSHOCO, okay? Power System Operation and Control, Operation Company, okay? Power System Operation Corporation, something like that. So this POSHOCO actually looks at all these operational aspects in the regional, in every region. And then we have one national level load dispatch center that is called National Load Dispatch Center, NLDC, which is located at Delhi. Okay, so these system control centers generally, they are the, we can say they are the state load dispatch centers. Okay, and of course they also give control, they do control of the transmission, state transmission utilities and state generating utilities. Okay. Okay, so let us talk about the basic concepts and definitions of power system stability. What is the meaning of power system stability? So already you might have studied in your basic courses in BTech and your MTech courses, right? So power system stability is the ability of an electric power system for for a given initial operating condition to regain a state of operating equilibrium after being subjected to a physical disturbance. Okay. And with most of the system variables bounded so that practically the entire system remains intact. So this is the definition of basic definition of our system stability. When the system is subjected to some disturbance, it should achieve another operating condition or another or the same operating condition, but it should regain the equilibrium state. That is very, very important, because achieving the stable equilibrium point is important in the power system stability. So when it achieves the stable equilibrium point, but achieving the stable equilibrium point is very important, where the system variables remain bounded and the system remains intact. Okay, so this is power system stability. So the disturbances mentioned in the definition could be faults, load changes, generator outages, line outages, voltage collapse, some combination of these. So many ways the disturbance may happen. Many times the load change takes place. The generator outages happens, line outages happens, sometimes the faults happen. In many ways we get the disturbance. So so some disturbance is going on. So is it audible?
Yes, sir.
Yagya?
Yes, sir. Yes, sir. It is audible.
Okay. Some network problem is there. Okay, no problem. Okay, so power system stability can be broadly classified into rotor angle, voltage, and frequency stability. So they're broadly classified into rotor angle stability and sorry, and voltage stability and frequency stability. Okay. So each of these three stabilities can be further classified into large disturbance, a small disturbance, or short term or long term. So based on the duration of the for duration of the stability issues, they're classified into large disturbance, small disturbance, or short. This is the classification of our system stability. So large, the broad classification is rotor angle stability, frequency stability, and voltage stability. And rotor angle stability is further classified as small disturbance angle stability, transient stability, and they both are under short-term stability criteria. They are under short-term power system stability. And frequency stability can be short-term or long-term, both. And voltage stability, of course, large disturbance voltage stability, small disturbance voltage stability, and they can be short-term or long-term, both. So we'll talk about what is small disturbance stability and what is transient stability, and or we can say what is large disturbance stability. And also again we'll talk about the short-term and long-term stability. So So all these three stability issues, they're interrelated, they're not independent of each other. So let us talk about the rotor angle stability. It is the ability of the system to remain in synchronism when subjected to a disturbance. Okay. So the rotor angle of a generator depends on the balance between electromagnetic torque due to the generator electrical power output and the mechanical torque due to the input mechanical power through a prime mover. So this is actually under normal operating condition, the electromagnetic torque generated, net electromagnetic torque should be equal to the mechanical torque, input mechanical torque given to the system by the prime mover. So remaining in the synchronism means that all the generator's electromagnetic torque is exactly equal to the mechanical torque in the opposite direction, right? If in a generator the balance between electromagnetic and mechanical torque is disturbed due to disturbances in the system, then this will lead to oscillations in the rotor angle. So if there is some disbalance, so till this equation is satisfied, T is equal to Tm. Up to that point, there is no disturbance, the rotor angle remains stable. So as soon as there is disturbance, the rotor angle starts oscillating, right? It will disturb, right? So therefore, we'll see in detail in the classical analysis how it happens, right? The balance between electromagnetic and mechanical torque is disturbed due to distance in the system, then lead to oscillations in the rotor angle. Then rotor angle stability is further classified into small disturbance angle stability and large disturbance angle stability. Okay. So what is small disturbance or small signal angle stability? It is the ability of the system to remain in synchronism when subjected to small disturbances. This is called the small angle stability, small signal angle stability. And if a disturbance is small enough so that the nonlinear power system can be approximated by a linear system, then the study of the rotor angle stability of that particular system is called as small disturbance angle stability. Okay. So the small disturbance angle stability generally it is taken care of by just linearizing the system because of the approximation, because in the small disturbance there is a small change in the rotor angle. So considering this approximation, the linear model is considered. So small disturbances can be small load changes like switching on, off, or of small loads, line tripping, small generator tripping, etc. Due to small disturbance, there can be two types of instability: non-oscillatory instability and oscillatory stability. So non-oscillatory stability is one which is really unbounded, and non-oscillatory instability. And oscillatory instability is oscillating is in nature and it is bounded. In non-oscillatory instability, the rotor angle of a generator keeps on increasing due to a small disturbance. And in case of oscillatory instability, the rotor angle oscillates with increasing magnitude. We'll see it very clearly. We'll discuss these things through some demonstration when we'll talk about the classical methods. Okay. Then large disturbance or transient angle stability. So it is the ability of the system to remain in synchronism when subjected to a large disturbance. So what is large disturbance? It can be a fault, switching on or off large loads, large generators, tripping, etc. This is called large disturbance or transient angle stability. When a power system is subjected to a large disturbance, it will lead to large excursions of generator load angles. How it will happen. because of this large disturbance, there is an unbalance between the torque, electromagnetic torque, and the mechanical torque. Because of this unbalance, the rotor angle actually moves, and there is large excursion in the generator rotor angle, and then it starts oscillating. So we'll see that. Since there are large rotor angle changes, the power system cannot be approximated by linear representation like in case of small disturbance stability. Cannot consider the linear approximation because there is a large excursion in the rotor angle. So the time domain of interest in case of disturbance as well as small disturbance stability is anywhere between 0.1 to 10 seconds. So therefore, this is known as short-term stability. Due to this region, small and large disturbance angle stability are considered to be short-term phenomena. These are considered as the short-term phenomena. These are not long-term phenomena. Voltage stability. So voltage stability also, it is the ability of the system to maintain the steady acceptable voltages at all the system buses when subjected to a disturbance. If the disturbance is large, then it is called as large disturbance voltage stability. And if the disturbance is small, it is called as small disturbance voltage stability, right? But unlike the angle stability, voltage stability can also be a long-term phenomenon. In case of voltage fluctuations occur due to fast-acting devices like induction motors or electronic drives, HVDC, etc., then the time frame for understanding the stability is in the range of 10 to 20 seconds and hence can be treated as short-term phenomena. So 10 to 20 second phenomena are called short-term phenomena, and the time range loading of the lines, generators hitting reactive power limits, tap changing transformers, etc., then time frame for voltage stability can stretch from 1 minute to several minutes. Okay, so therefore this is known as long-term voltage stability. Okay, so the main difference between the voltage stability and angle stability is that voltage stability depends on the balance of reactive power demand and generation in the system, whereas the angle stability remains mainly depends on the balance between real power generation and the demand. So there is a huge difference in the concept of reactive power and reactive power and real power. So reactive power is a concept which actually we cannot use the reactive power. It is essentially required in the AC system, AC transmission system. But this reactive power balance is means that the instantaneous reactive power generated must be equal to the instantaneous power that is consumed. Okay, or instantaneous reactive power stored, that is the instantaneous reactive power exhausted. That is the phenomena, because average reactive power is always 0. So whatever reactive power formula we know, Vi sin phi, it is the maximum value of the reactive power. So therefore, it is very important that the concept of reactive power is completely different than the concept of real power. So, so in voltage stability issues, it will be taught. Coming to the frequency stability, it refers to the ability of a power system to maintain steady acceptable frequency following a severe disturbance between generation and load. Okay, so it depends on the ability to restore equilibrium between system generation and load with a minimum loss of load. So frequency instability may lead to sustained frequency swings, leading to tripping of generating units or loads. So during frequency excursions, the characteristic times of the processes and devices that are activated will range from the fraction of seconds, like under frequency control, to several minutes. So therefore, this frequency stability can be short-term phenomenon and long-term phenomenon. Okay, so based on the disturbance and the action taken and how fast it recovers, based on that, this phenomenon, long-term and short-term, they're categorized. The stability is classified into rotor angle, voltage, and frequency stability. They need not be independent, isolated events. A voltage collapse at a bus can lead to large excursions in the rotor angle and frequency. Similarly, large frequency deviations can lead to large changes in the voltage magnitude. So they are not independent of each other. One stability phenomena may affect the other stability phenomena. So therefore, simultaneously assessing the stability phenomenon is very, very essential. So component of the power system, that is power prime mover, generator, rotor, generator starter, transformers, transmission lines, load controlling devices, and protection systems should be mathematically represented to assess the rotor angle, voltage, and frequency stability through appropriate analytical tools. This is very important because unless we have a mathematical model of the system, it is very difficult to assess the dynamic stability assessment. And therefore, we need to first model the system properly. So we'll talk about in detail how to model the system after the classical approach, after the discussion of the classical approach, because classical approach we don't require any model. It is just based on certain assumptions, right? In fact, entire power system can be represented by a set of differential algebraic equations through which system stability can be analyzed. So this is very important aspect. When we can model the system with some differential algebraic equations, we can easily assess the system stability. Okay.